I think we had discussed this thing, right? Yes, I think. So advantages of laser diode, I think we had discussed. Yes or no? I'll recall once again. So the advantages of the laser diode, it is a simple economic design. Compared to LED, this is a bit complex, but we can say that this is simple. As you all know, this it has got high optical output. Why it has got high optical output? It is just because it is not just like LED, where in LED it is a spontaneous emission, whereas your laser diode has got stimulated emission, so it is amplification will be done, and hence you will be getting a high optical output. Okay, high optical power you can achieve high optical power. Production of light can be precisely controlled. So here your whatever the emission of photons, that can be controlled precisely. So how you can control it is all because of its stimulated emission. So all the other phases. So if I show the later things, you will come to know the diagram. There you can link. So all the other surfaces will be closed one side. So with which we can control precisely, and everything will be focused on a single direction, just like your edge emitting LED. This can be used at higher temperature, and you can achieve a better modulation capability, high coupling efficiency, low spectral width. So these 2 points, I think, while explaining LED, there only I had mentioned you the laser diode. That is the radiation pattern of your laser diode, whereas it is very directional. As you all know, this laser diode is a directional one, and I can say is uh, the response time, the spectral width is very less, and it can connect to very, that means it has got a smaller core, all those things. So due to which better this thing, high coupling can be done. Coupling will be efficiency increases, and the spectral width also will be less, and ability to transmit optical power between 5 and 10 more, because it is a stimulated thing. So this disadvantages, I think, at the end of this fiber, there will be a speckle pattern. So that appears at two configurant, I can say, coherent beams, due to which either it is going to add or subtract its electric field depending upon their relative phases. So this laser diode, this is extremely sensitive to overload currents. While explaining the differences between LED and laser, I'll tell you this sensitivity, how it is related, and at higher transmission rates. So since it is laser, it has got higher transmission. Laser is required to operate continuously, due to which there will be use of large drive current. Okay, so due to this large drive current being generated, so there is some thermal actions takes place. Okay, which is, it might be unfavorable, and due to which you might require it requires cooling and power stabilization. Next is lasing action. So what is this lasing actions? So as you all know, this lasing action, it is explained, as well as this is also called as a fabric resonator. Yeah, I think it is normally a fabric mirror. So it is you as and when your spontaneous emitted photons, it what it does, it makes back and forth motion in the cavity. So what is this cavity? Cavity is the in between. That is the active region. Active region. This is a PN junction. In between, it will be having a active region. Active region. Here, it is going to the photons which is been liberated. It moves back and forth, and then again it in turn generates new photons. So due to which a stimulated action is going to get achieved, and fourth, and with due to which I gain in energy in the power current characteristics. I tell you how this current increases sharply. That I'll tell you there. Okay, these laser are just like an oscillators. Oscillators. They will be operating at a frequency f. For example, it is considered as a oscillator. Okay, how this oscillators? This oscillator, how it is formed? This oscillator is formed with a resonant cavity, providing a selective feedback. So, providing a selective feedback. So, the cavity is normally a fabric product resonator. So, what is this fabric product resonator means? Here you can consider this P and this as a N. Okay, these two acts as a parallel plane mirrors. So, which will be separated by a distance distance of L. L. So L is the distance from here to here. It is a distance L. L. So the light propagating along the axis of the interferometer, it will be reflected by the mirrors. So it will be reflected because once it hits, again it comes back, right? So there it is going to generate new photons by the mirrors. Here you are saying mirror. So back to the amplifying medium. Amplifying medium is the active region providing optical gain. So here the dimension of this cavity, it will be 25 to 500 micrometer longitudinal, lateral and transverse. That is 1.1 to zero point 0.2 micrometer transverse. Here, here you can see a single layer junction, single junction confinement. So in the you can add one more on top of these two, top and bottom, one layer extra. So that forms two heterojunctions. So these two heterojunctions with the addition of these junctions, it is going to provide a carrier and optical confinement. Optical confinement. So what is this optical confinement? Confinement to the junction. So the current at which lasing starts, that is called as the threshold current. So the lasing action. So as and when it goes, hits and liberates photons. The photons again hits and again it liberates it. So that process we call it as an lasing action. So whenever, as I said here, it moves back and forth motion. So due to which it gains energy. So that I'll tell you in this. Here you can see the characteristics. Okay, so this is what your lasing action. So after which it is very steep, very steep. Okay, that is what your lasing action. Once this lasing action starts, the threshold current increases. Above this current, the output power increases sharply. Okay, here you can see the field distribution in different directions. For example, that is the lateral direction, the transverse direction, and longitudinal direction. You can see the transverse direction as well as the lateral direction, how the field pattern varies. So here distributed feedback laser. So here you can see in this DFB distributed feedback laser, the lasing action, it is going to be obtained by the periodic variations of the refractive index. It is all rest all same. Here you can see the fibrin gratings. Okay, so this fabrication is similar to your the previous one. The only thing is here it is obtained due to the periodic variation in the refractive index in this there. So this is incorporated into multi-layer structure along the length of the die. So through the entire length here there will be a variation in the refractive index due to which the generation of your what I can say is photons will be varied. So it will be distributed based on the variation in the refractive index. Fine. So this will be incorporated. As I said, here this two, this will be the active layer, this will be NP. So this confinement layers, these two and other these two. So this will be PN junction, on top of which again you will be having. So these things, what they will do, they will confine the photons liberated, so that everything gets confined and it will be passed through a single outlet. Like, so here the modes of laser diode. So it can be, as I said in the previous thing, it can be longitudinal mode, lateral mode, transverse modes. It can travel. So the electromagnetic wave that is propagating in the longitudinal direction, it is expressed as E of ZT is equal to E of Z into e to the power of. See here I have just written E into J, right? Actually, it is E of Z T is equal to I of Z into e to the power of j of omega t minus beta z, where I of Z is the optical field intensity, and here omega I have missed here. Omega is the optical radian frequency, and beta is the propagation constant. Okay, so the modulation of optical bandwidth. What is this modulation of optical bandwidth? See, the optical bandwidth here you can see uh, what I can say is this modulation of optical bandwidth. This whatever the this is generated, it will be having both your optical bandwidth as well as electrical bandwidth. So, electrical bandwidth, you know how to calculate. It is 1 by root 2. Root 2 1 by root 2 is how much? 0.707. 0.707 times of this. So if you take, for example, this is on the curve, it will be just like a low pass, like, so initially it will be just like this, and later on it will increase down and decreases down like this. So here I was explaining. So it is, you will be taking 0.707 times this. So this will be your electrical bandwidth. Whereas your optical bandwidth, it will be 0.5 times this thing. So it will be below this. Okay. This modulation of optical bandwidth, it all uh, depends upon the injected injected carrier strength, injected carrier strength. As you all know, based upon your injected carrier strength. Suppose if we inject only a single radiation or single photon into the what I can say is, so if the photons that is a incident on the materials, that it generate liberates or energy, so it is going to shift from one energy level to the other energy level. Again, it is going to lead from that is the emission takes place at that time, it is going to stimulate. So like this. So suppose if more light is incident, so that is what injected carriers. Okay, and again it's carrier lifetime. So carrier lifetime. If carrier lifetime is more, then the number of photons liberated will be more, and hence in turn you'll be gaining a higher strength power output. Okay, and also doping level. If your doping level is that means if you have more what I can say is, if you have more electron hole pairs, if you have more electron hole pairs, then you obviously it creates more transitions, and hence you will be having a more output. Okay, that is what doping level uncertainty. Next comes your power current. Suppose if we plot current versus optical power, then Here you can see. So initially, as and when your photons or this it hits the object, it is going to be liberate, liberate. Uh, Second, it is going to liberate. So if it is going to, there will be an emission. As and when it is going to absorb, it is going to leave some, or it is emission will be taking place. That is spontaneous emission. It is just like your what I can say is like your LED. Once after is that your lasing actions takes place, then it is increased steeply, which we call it as a stimulated emission. So this is what your power cuts. Initially, it acts as an LED. Later on, after lasing action takes place, lasing action takes place, you will be getting highly or a steep. There will be change in a I. That means your emission will be more and it increases steeply, very high. More number of photons will be liberated, due to which high optical power will be achieved. Next, the comparison of LED with your lasers. So the principle of operation, as I was already telling you, it is spontaneous emission, whereas this is stimulated emission. What is spontaneous emission? What is stimulated emission? Already we have discussed. So the output means non-coherent, and here the laser diode it is coherent. So what is this non-coherent and coherent? Can anyone tell me? Can anyone tell me what is non-coherent and coherent? Can anyone tell me what is non-coherent and coherent?
Sir, hello.
Yes, yes.
Sir, coherent ಅಂದ್ರೆ ಒಂದೇ frequency like similar type ಆ ಥರ.
Okay, good. ಇದು non-coherent ಅಂದ್ರೆ
Sir, different.
okay. So what is this coherent ಅಂತಂದ್ರೆ? See, the coherent means whatever the emitted photons, so all those things will be having same same phase, or a constant phase will be there. Whereas non-coherent is not like that. So here, for example, if you understand the spontaneous emission, there you will be coming to know that there the emitted photons it will be randomly in LED, that is in the spontaneous emission, it will be random. So the phase and this thing will be different from each thing, but here it will be coherent. That means the phase difference it will be constant here. That is what. So the spectral width, as you all know, it has got a broad spectrum. Here it is very much narrower. Okay, and the data rate is very less, and here it is very high. Why? Because because it is a spontaneous emission where only small number of photons will be emitted. Here, more number of photons. Hence, it is monochromatic, and you also know that it is monochromatic, highly coherent. That is what. So the transmission distance. Sorry. The transmission distance is smaller, the LED, compared to your laser diode. It is smaller, whereas the laser diode it is very large and greater. Okay, so temperature sensitivity, it is less sensitive. This is more. Fine. Next, coupling efficiency is very low. Why you all know? Huh? And this one. Whereas here it is high. Why it is high? Because here it is very low since it is disperses in the lung. The spectral width is very large, or the radiation pattern is very large. Here the radiation pattern is very large, hence coupling will be more. Okay, compatible fibers. So which are all the compatible fibers to work with your this thing? So it is multimode, step index, multimode, gradient index. Here, since it's a laser, it is single mode, step index as well as single multimode, gradient index. So circuit complexity, this will be always simple and it is complex, as you all know. So the lifetime it is 105 and it is 104 hours. So it is a comparison that is done very long back. But the lifetime nowadays, LED and laser, it is very high. The cost is very low and this is high compared to your LED. So the output power is linearly proportional to the drive current, whereas this is proportional to the current above the ratio. As you all just the current power characteristics I had told you there. Whatever the current required is the current required is the drive current required is 50 to 100 milliamps milliamps, whereas here the threshold is 5 to 40 milliamps. So application is for lower data rate and moderate distance. For whereas laser it is for a longer distance, high data rate and all. Okay. So with which optical sources were finished, we have finished optical sources. Next comes your optical detectors. So what is this optical detectors? That we'll see in the next. Okay, is that fine? What on Anubhav? Shall we continue in the tomorrow's class?